as good when I do it, but at least I'll have a video if we need it. And let me hide this. But I don't have to worry about the screen. I don't have any issues with that. So far, everybody's fitting on here. Before I start, does anybody have any questions about anything? Any concerns? Blurry Jack, yes. Jack, do you have something to say, or did you just wanted to raise?
Oh, yeah.
Yeah.
So how do you do the table? I was really confused.
Okay, we'll go over that in a minute. We'll after the warm up, we can go over that first thing. Any other general questions? All right. Well, so this I've got a video here, and in the past when I've tried to show videos while I'm streaming, sometimes it just doesn't work very well. So hopefully it'll work, and it's better than me just talking about this. And in the warm-up I say, suppose a skydiver steps out of a stationary helicopter, falls until reaching terminal velocity, and so on and so forth. Does the usual parachuting thing on the way down. In this video, it'll be somebody stepping out of a plane, but in my scenario, it's a helicopter because I want the person to be totally still in the beginning. And it's kind of funny, if this video works, you can see in the picture on the right, this is a screenshot from it. A lot of times they have the speed of the skydiver in meters per second, and they start the skydiver's speed out at 0 meters per second, which has got to be false unless the plane is flying into a 100 mile per 100, unless the plane is flying into a really fast headwind, because otherwise a person's going to have some forward velocity and their speed shouldn't be 0. So they're just doing the speed in the y dimension, which is what we would see if this was a helicopter. So I'll play this. I may be tempted to interrupt it, but I may just let it play through. Hopefully it'll work. Let's see. If you can't hear or something, shout out.
When a skydiver jumps out of a plane at
Can you hear him talking? Okay, good.
3,000 meters, her speed goes through some big changes. So what's happening to the forces as you fall through the air? The force of gravity is always trying to pull us towards the Earth. Before the skydiver jumps, the floor of the plane provides a counterforce which balances the downward force of gravity right up until the moment she steps out. Gravity immediately pulls her towards the ground, and she starts to accelerate downwards. But air resistance is acting in the opposite direction. The faster she falls, the greater the air resistance. Eventually, the upward force of the air equals the downward force of gravity. When forces are balanced, the speed remains constant. That doesn't mean she stopped falling. It means she stopped accelerating. She's still doing a steady 55 meters per second, and hitting the ground at this speed isn't a good idea. To slow down, the upward force needs to be greater than the downward force. When the parachutes open, air resistance suddenly becomes much greater than gravity. The forces are no longer balanced, and this changes her speed. She slows down. Because she's slowing down, air resistance decreases until it balances gravity again, and she reaches a much slower constant speed. Approaching the ground at 5 meters per second is a much better idea. As she hits the ground, there's a thumping great counterforce from the Earth, which decelerates her very quickly.
All right, I don't think they do anything interesting or worthwhile after that. So on the test that's coming up, there are going to be a few questions where you have to draw force diagrams, and it'll be a series of force diagrams. And this is going to be one practice exercise, like something that might be on the test. So hopefully you've got a pencil or paper or something that you can draw some pictures on. This says to draw one force diagram for the beginning of this trip. So just assume somebody steps out of a stationary helicopter, falls until reaching terminal velocity, just like the skydiver did, deploys a parachute, reaches a new terminal velocity, lands on the ground, and then stands still after that. Just like in the video, except I don't know if we saw her standing still. So we'll draw one diagram for the very beginning of the trip. This would be not when she's sitting in the plane or the helicopter in this case, but at the moment the skydiver just releases from the plane. And then we're going to do another diagram representing 2 seconds into it. So this would be before, this would be while the skydiver is still falling and speeding up. And then after that, I'm going to want you to do a new force diagram for every instance when the net force switches between positive, negative, or zero. So the skydiver's falling from the sky. There are basically, there's weight, there's drag, and those are the only two forces. And between those two forces, we're going to get a net force that's either upward, positive, or downward, negative, or neither, zero. And that's going to flip-flop various times during this fall. So if we do one in the very beginning, as soon as she releases from the plane, another one a couple seconds later, and then another diagram every time the net force switches, either like it's positive and then it goes to negative, or it's negative and then it goes to positive, or it's zero and then it goes to positive. That's what we're going to do. So we'll do the first couple together, and then I'm kind of curious to see if you can tell me how many this is going to take, how many diagrams this will need in all. So I'll show you. I'll do the first couple just to explain what I'm talking about. Probably have to unplug and replug my camera here. Come on, camera. There we go. And just for anybody who's watching the video, this will be so they won't be so lonely. Can't move myself around like I usually can. Okay, so the first diagram is, this would be right after she jumps out of the plane. Got the backpack on with the parachute in it. And at this point, I want to draw all the individual forces, use arrows for those. We don't really know what the numbers are exactly, but they should be kind of sensible relative to one another. And then I want to have the net force. So in the very beginning, how many forces are acting on the parachuter? Show me with hands. Is it 1 or 2 or 0? So there's always weight, and the other force that there may be is drag. But in the beginning, when this person really has just started to fall, there's no drag. So this would be it for, I'm just going to number this. This is 1. This would be at time equals 0 seconds. And the net force would be same as weight. So that's the net force. Now, after a couple of seconds, which way is the net force going to be? Up or down or no net force? What do you think? Somebody falls, somebody steps out of a helicopter, falls for 2 seconds, continues to fall after that, but at the 2-second mark, is this net force going to be up or down or 0? What do you think?
Isn't it down, but not like greater than what it is at 0 seconds?
Right. It's going to be less than what it is now, but it's still going to be downward. And the thing that's changed is not the weight. The weight of this skydiver, this will be constant the whole time. The weight's never going to go away. The only way for weight to go away is if this person loses a piece of the backpack or gains some more mass somehow, or if gravity changes significantly. So weight's going to be the same. But now there's going to be a little force of drag. And I'm just going to call it F subscript D for drag. And so the net force is going to be down, but not as big as it was before. It's going to be however long I draw this minus the length of however long I draw that. And it's possible, given some kind of weird shape of this person, and if this person were maybe a wiffle ball or a feather, then drag might already be as strong as weight. Yes, Kat. Riam. Okay, Riam. Question? Riam? Riam? All right. If you can, if you have, just butt in, Riam, if you want to. Oh, what?
Okay. Should you always show how big the force of drag is, the force of weight, like it was shown in the video?
Oh, right. So in the video, they were just showing these two. They had, I can't remember, was this a green arrow and then a red arrow? That would make sense. Like the green speeds you up, the red slows you down if you're falling. They didn't show net force, which would be this one. Well, it would be these two added together. And in this case, this is a bigger negative than that is positive. So the sum is a negative. So these are the arrows they had in the video. But we're adding in net force too.
Okay.
So my question for you is, how many more diagrams are we going to need to draw? This starts right here, and it ends when the person is just standing on the ground. So the last diagram we're going to draw will be somebody standing. This person's standing on the ground. But you'll do a new diagram every time this switches, either from down to up, or down to 0, or 0 to up, or 0 to down. Anytime the sign of this changes or becomes 0. So think about that. Just try to visualize the flight down, doing basically what the person did in the video. And the question is, how many more diagrams do you think we'll have to draw after this? We've already done 2.
Would it be 2 more?
2 more? More than that. Do it. Write in the chat how many you think, and I'll see how many people get it right. Claire says 3 or 4. I'm not telling yet. David says 4, 3, 4, 5, 3, 4, 5. All right. It's looking like the average is around 4. I think it's 5. Now, I could be wrong here too. But it should be, when I was thinking about it earlier, there should be 7 altogether. So this would be, you don't have to write what I'm writing down. I'm just trying to explain what's going on. This is, well, I don't even think I'm going to write this. This person would be speeding up and going down. Now, this is going to change. The net force is going to change as which one of these forces changes. There's only one that can change, and that's the force of drag. And if the net force is down, this person's going to accelerate downward and go faster and faster and faster. So this is going to get bigger and bigger until it becomes the same as that. So that's the next picture. Because when I'm drawing this person in an odd order. When the force of drag is the same as the weight, then the net force is 0, and that would be terminal velocity. And in the video, the terminal velocity was 55 meters per second. which for a skydiver, that's kind of average terminal velocity. It's about 120 miles per hour. So if this person doesn't do anything, they're gonna stay at that. This is just they're gonna hit the ground going 55 meters per second. Right. So my next one, in the video, what changed next? Was it the force of drag or the weight? And what happened to it? Or what event caused this terminal velocity, this constant speed to suddenly change? Canizaro.
When he releases the parachute, then the drag is hot.
Right. Right. So when that parachuter pulled the cord and this started to come out, I don't know, it could have been the moment it just started to unfurl or when it totally opened up. Then there's a lot more drag. So the force of drag is suddenly bigger than the weight, so the net force is up. And this wouldn't cause the parachuter to stop. It just causes upward acceleration, which means this terminal velocity was dropping. So we've got an upward net force. In the next picture, what's the net force going to be? Claire.
It's going to be larger.
So if this was if the time, I'm just making this up, if the time was 10 seconds and then the next one was where the time was 10.1 seconds, you would be right, because this parachute would probably open up more and it would be nice and broad and that would give more drag, so you'd have an even more upward force. But if we're just drawing these every time this changes, this either needs to change to downward or zero. Which one's it going to be next? In the next picture, what's the net force going to be? When it's no longer up, what will it be?
0.
0. And the reason it's going to be 0 is because as the parachute opens up, and let me draw this. The weight's got to be the same. The parachute and this upward acceleration, this is going to slow the person down. The person's falling downward, so the upward acceleration is going to slow them down. So eventually the slowing is going to decrease the force of drag. Once this is fully opened, it's going to slow down, slow down, slow down until it's going slow enough that the force of drag is equal to the weight again. And then we'll be at terminal velocity again. But it'll be a different kind of a balance this time. This time the terminal velocity, I think, was 5 meters per second for that 5 meters per second for that particular skydiver. And how fast this is depends on the size of your parachute. If you feel like hitting the ground at 5 meters per second is too fast, then you could design some kind of bigger parachute. Or if you want to get to the ground faster, then you make a smaller parachute. All right. So now the parachuter is just drifting to the ground. The next time this changes, what's the net force going to be? Is it going to be positive or negative? In my next picture, I'm going to draw a picture of what it's going to be when it's no longer 0.
Positive?
What's that, Riam? Positive? Yeah.
Mm-hmm.
And Riam, what's going to cause this to become positive?
The acceleration.
The acceleration and what's going to apply a force that's going to cause that positive acceleration?
Upward.
What's that?
Because the net force is going upward.
Yeah, and I actually misspoke earlier. I was saying that in these diagrams we were only going to have two forces, the force of drag and the force of weight. But actually in this next one, it's a different force. I'm just going to flip my paper over. And the next time the net force is going to flip-flop, it's going to become upward, is when the parachuter hits the ground. So the parachute, I'm going to show it just kind of losing its steam here, and the force of impact from the ground, I'll call it the normal force, surface pushing down or pushing up, is stronger than the person's weight pulling them down. And this is while this is happening, this is going to cause the person to slow down from 5 meters per second to 0. In the very last picture, number 7, what's the net force going to be then? I'll just go ahead and draw the person here. What's the net force now? Should be 0. We've got weight, and we've got the normal force, and the person's just standing still, so they should be even. So we'll do some more practice with things that aren't objects falling from the sky, but if you watch that other video that I mentioned last class, and then on my website I actually said I may have to cut class short, watch this video and do the skydiver graph. It starts at 32 minutes. That's kind of the same. This is just a different way of getting at talking about what's happening to net force over time. You could do it as a series of pictures with diagrams, or you could show what's happening to net force. I kind of like this better. We'll do some more practice with this later on. But if you want to see the graphing version of that, I put another link today on my website. This video started at 33 minutes, and it'll take you through basically the same thing, but a different way of seeing it. So Jack had a question about the homework, the graph, or the table on the homework. And I'm going to get that out. What we just did leads into that nicely. So, Jack Canizaro, this is what you're talking about, right?
Yeah.
Yeah, okay. Oh, by the way, so all the people who said 5, you were right. And if you didn't say 5, it's no big deal. So we have, here's the timetable first. Parachuter steps out of a plane. This really should be a helicopter. Parachuter reaches terminal velocity of negative 55 meters per second, then pulls a cord. So terminal velocity is reached after 10 seconds. They're just falling at terminal velocity for another 80 seconds. At 90 seconds, the parachuter pulls a cord and the chute deploys. So the chute's coming out. By 98 seconds, 8 seconds later, the chute has slowed the person down, and this person's at a new terminal velocity of negative 3. So this is a slower parachute than the one in the video. And then for another 400 seconds, it's just a nice float down to the ground, and the parachuter lands. And you have to fill out this table. So the masses are all easy. Mass is just going to be the same the whole time. Weight is just mass times gravity, so this times 9.8. And normally you don't write negative for the weight, but I decided that in the context of this table, showing weight as a negative or downward force is helpful. So this is the weight of the parachuter. This is the 980 newtons acting downward. I guess I could draw this. So here's the parachuter. Weight always going to be 980 downward. And there's going to be some kind of force of drag acting at times. So in this first column, or first row, at 0 seconds, that's when the parachuter steps out of the plane. At that point, there is no drag. So drag is 0. And if drag is 0, the net force is 0 minus 980, which is just negative 980. And the acceleration, so if F equals ma, then A equals net force over m. So you could take this net force, divide it by 100 kilograms, and you get negative 9.8. Or you could just say, if there's no drag, then this is free fall, so the acceleration is negative 9.8. And and the velocity is 0. 5 seconds gets a little trickier. At 5 seconds, that's right in between here. We're not at terminal velocity yet. We're given the velocity, so it's speeding up downward, but not quite to negative 55. The weight's still going to be the same, but now there's drag. There's 500 newtons of drag. So if this is 500, then 500 up minus 980 down gives us a net force of negative 480. So that's why I put the negative here. So I could just say these are the two forces acting on the person. If I add them up, that gives me the net force. And the net force, right here, divided by the mass, negative 480 divided by 100, gives me the acceleration. Next part, 80 seconds. So 80 seconds is between 10 and 90. At 10, the parachuter reached terminal velocity, and at 90 pulls the chute. So at 80 seconds, this person would still be at terminal velocity. That's how I know the velocity is still negative 55. It's going to stay there until something changes. And if you're at terminal velocity, then we know a few things. The force of drag has to be equal to the weight, and there has to be 0 net force. So anytime we're at terminal velocity, there's 0 net force, there's 0 acceleration, and the force of drag is equal and opposite weight. Then for 97 seconds, so this is between the time when the parachuter pulls the cord and when the parachute has fully slowed down to the new terminal velocity. So now we've just got to take into account this extra information. So there's the chute is coming open, and that's creating this really big upward force. The force of drag is 1200, which is stronger than the weight. So if you add 1200 to negative 980, you get a positive acceleration, or sorry, positive force, and divide that by mass to get the acceleration. Speed's already given. And then finally at 300 seconds, we're at terminal velocity again, because terminal velocity is achieved at 98 seconds. So anything after that, before the landing, is going to be at terminal velocity. So that tells us net force is 0, the acceleration is 0, the force of drag and the weight have to be the same but opposite. And then since we're given the terminal velocity there, it's still going to be the same. Any questions? All right, so there were some other ones here. Oh, wait. Yeah, I guess this was... No, you weren't supposed to do that. Your assignment was to do these. And I can open up the answers to them. Did anybody have questions on any of those? Anything you want me to go over? And Riam and Jack, put your hands down. Claire, is that a new hand or is that an old hand? New hand?
New hand.
Okay. What's your question, Claire?
For number 2, would there have been different options for like this scenario? Or was the answer you were looking for, like specifically the one that you had on the answer key?
Yeah, hold on for a second. Let me open that up. Sorry, I know, just worried I'm going to open up the wrong thing. Oops, here's the lag. Okay, so this is the... Are you saying, could there be a different answer than this? Is that sort of... The answer is yes. I suppose you could answer it in multiple ways, but the trick is, if you're in space and you want to measure mass, you can't use weight. So on Earth, you could put something on a scale, and the gravitational pull will smash it into it, or smash the object into the scale, and that will be proportional to the mass. But if you're in outer space, where there's really no gravity, you have to use some other way to test the inertia, basically. And both of these methods are really using a version of F equals ma. You're kind of applying a force and seeing what kind of acceleration you get. So if you apply a force and you get a really big acceleration, then you realize that the mass must have been small. Or you apply a force and you get a small acceleration, you realize the mass must be big. Do you have a different answer to propose?
I realized that I read the question wrong.
Okay.
I created a scenario as if it was on Earth.
Oh, okay. So yeah, if it's on Earth, you can put it on a scale. But then there may be other ways to do it. You could shake it, you could push it. I don't know. I can't really think of anything other than applying a force to these boxes and just sort of feeling what happens to you and to the box. Other questions about any of these? 1, 3, or 4?
Can you go over 4?
Sure. Yeah, 4 always gets people. Just the idea that if you're standing on a flat surface, on a barge, on a skateboard, in a car, in an airplane, whatever, if the plane slows down or if the car slows down, well, not really a car. A car's bad. If you're standing in the back of a truck and the truck slows down, it's friction that's slowing you down. Last term, I think I hammered that home too much. And I think what I would say here is this diagram that I keep caressing with my mouse, I could have just as well written, instead of force of friction equals 200 newtons, I could have just called this the force of the barge pushing the person. But it's probably better to write friction here because the barge is really pushing the person two ways. The barge is pushing the person straight up, and then the barge is pushing the person sideways using friction. So that's just this idea of friction. That's usually the most confusing part. Let me step back now and just look at what was given. So it was a 100 kilogram person, and the acceleration of the barge is 2 meters per second to the right, and the person's accelerating with it. So the person has an acceleration of 2 meters per second. Draw all the forces. So when you're drawing all the forces on the person, the first thing to think of is weight. Draw the weight. And if the person's not falling or something, as long as they're not in the sky, free falling, then there's going to be some other opposing force. It's probably going to be drag, or it's going to be tension, or it's going to be a normal force. So in this case, it's the normal force. And since the person's not going up or not going down, person standing on a surface is going to have a normal force equal to the weight. And then the last thing, even before you start labeling this other force or thinking about it, you could just look to the acceleration. Just the fact that we have an acceleration that's 2, it's positive, means there has to be a net force. And I can calculate that over here. That's what I've done with Newton's second law. The net force equals mass times acceleration. It's 100 kilograms times 2 meters per second squared. That gives me a 200 Newton net force. And if all I had drawn was the weight and the normal force, that would tell me there's got to be something else. There's got to be a force to the right. And the only other thing that can be pushing this person to the right really is, I don't know, it doesn't say anything about wind or some other mysterious forces, but it would be the force of friction where they're standing on the floor. And so that has to account for the 200 Newton net force.
Would the force of friction be going to the left since it's accelerating to the right, or would it be going to the right?
Well, the person is accelerating to the right, and the friction is pushing the person. If you just imagine you're standing in the water out here, and you give the back of this barge a push to the right, that's going to push the person to the right also. That's kind of what's happening here. And if there were no friction under the person's feet, it wouldn't happen. You'd just push the barge to the right, and it would slip right under the person's feet, and they wouldn't experience any force. So it's definitely a rightward push. And as odd as that sounds, that means the person is pushing the barge which way? To the left. So if we were drawing forces acting on the barge itself, we would have to draw the force of the person pushing the barge to the left. using friction. But we're not drawing forces acting on the barge, just the person. It's kind of a confusing thing, but if you just stick to the fact that there's rightward acceleration, that means there's a rightward net force, that means you've got to have some rightward force, and there's nothing else here that can account for it. It's got to be friction. I'll give you some more practices like this over the next couple of days, or 3 days or so. Other questions? All right. So this is going to be a quick formal part of class. I just spent, well, not just now, but an hour or so ago, I spent quite a while going over these. These are your assignment. This is a good selection, variety of problems like we've done in this unit, like the kinds of things that are going to come up on the test. I went over all these and I explained everything, and I made 3 different videos. One video goes through number 4, one video goes through number 7, and then there's another one. You don't have to watch those, but I just want you to know those are there. I'm going to cut class off early to give you a little more time to practice this. This may end up being more than you want to work on tonight. I don't expect you to put in hours and hours of work on this. I don't really know how long it's going to take you. It depends on how polished you're feeling with all this stuff at the moment. So if you don't finish this assignment, you want to keep working on it tomorrow, that's no big deal. I just thought I would go ahead and give all this to you. So on my webpage today, this is a scan of the solutions, and then these are the links to videos if you want to hear me explain more than what's just in the solutions. But the solutions I wrote out pretty neatly. They're there. And in Google Classroom, I think I put everything there too, but let me check real quick. Oh, I did never assign this. Yeah, so I added these 3 things, and I guess I'll assign it now. I'm putting today as the due date, but you don't really have to have it done today. So that's it. I know Abby needs to take her test, but if anybody else wants to hang out here and just kind of work and I can be available to answer questions as you go, or about anything, that's fine with me. Abby, are you there? Okay. Abby, which section did you want to do?
3.
3? Okay. I'll go ahead and assign that in Google Classroom. And like I said, anybody else who wants to hang out and talk, Abby, you can just turn your speaker off if we're driving you crazy. I'm going to stop presenting for just a second. All right, Abby, it's there. Looks like it's just us. So
Yep.
I'll just hang out here. If you have any questions, just ask.
Okay, yeah, I'm gonna have to go downstairs to just like print it quick.
Okay.